All right, folks, here we go. Tuesday morning. All right. First and foremost, this is not fourth. It's actually the third. All right. So here we go. All right. Today we're going to talk through torque, and you can start to see some tangential velocity there in the little video on the bottom right there of some people flying off. I do not condone this physics, but do not go out to a local playground and let it rip like this. Okay. Anyway. All right. So here we go. Okay. So if you've ever used a wrench to tighten a bolt or a nut, meaning that, and you can even look at it like, have you ever used a hammer to hit a nail? Have you ever tried to turn a screw from a screwdriver or something like that? And we're talking about hand position, you know. So part A, we can see as close. Part B, we can see as far. So for us, we want to know which one is going to give us more quote-unquote twist. Well, part B should be able to, right? Even if you push just as hard at both places, it still should be part B, all right? This is one thing that I learned as a helper in the summertime of my college work jobs. I was pounding some nails, and I wasn't a big, kind of industrious kid. Through most of my middle school years and stuff like that, and the guy I was working with goes, move your hand down, and you'll be able to hit it a lot harder and do a lot less work. And I was like, oh, okay. And I found that was the case. Obviously, my accuracy wasn't good, but you can see some people who, can hit nails, and they hit them with enough force that they actually drive that nail halfway in with that first shot. That wasn't me. But anyway, all right. So if A and B are the same size, what's the only difference? So for us, the only difference between A and B, if they're the same size, is the force or the distance from that kind of pivot point or that location right here, right? So because that's the point where we're going to see this thing moving and twisting and turning, then what we're going to see is that distance becomes important, right? We're able to get a little bit more leverage on it. If you've ever seen people changing tires on cars without using the actual air gun, there are some that will use, very long kind of levers or wrenches or, something like that. What ends up happening is that they can apply a bunch more kind of force on it and get this twist to happen a lot easier, all right? Because the distance is pushed out, it allows that force to kind of multiply for us, so to speak, okay? So now, if we go out to point B again, right, and we look at this and we say, all right, the first one versus the second one, the 1 versus 2, 1 versus 2. Those of you who've ever been to an optometrist to get your eyes checked for glasses or contacts or anything like that will get that one. And usually for me, they had to go through the alphabet twice and then go through a series of numbers also after that because my eyes were so stinking bad. But anyway, all right. So if we look at the angle now, right, angle becomes important for us as well, right? If we see this angle, notice how it's straight onto it. Notice this one here, right? This becomes the scary one for us. I've had, to kind of sharpen lawnmower blades and stuff like that, and there have been times where I've been at this angle, and what happens is that the wrench slips off, right? It's a beautiful thing because usually you're working with a relatively sharp blade on the other side, so I've got scars on the top part of my hand and my knuckles from these lawnmower blades and me slipping off, right? Not all of my force is being directed there, all right? So we ask, will there be as much twist here? No, no, because our force is being misdirected, right? If we can get that force to be straight to it, now all of a sudden we see all of that force is being transferred to this twist. Here, some of the force is being transferred away from the twist. What we mean is that we're actually losing some of our twisting force, so to speak, okay? Angle makes a huge difference for us. We want to be as square to that as we can. The more we start to deviate, whether it's to the left or to the right or nearer to the wrench or farther away from the wrench, the more force now we are wasting, so to speak. Okay? So, torque. Torque is a twisting force. Kind of, right? Okay. Our symbol is tau. It's basically a fancy lowercase t. All right. You'll see me draw the top of it as a kind of curve and then do like a reverse J on it. All right. Our formula. Okay. So make sure here again, along with the tangential velocity, you've got this formula. So tau equals our perpendicular force times our distance. Perpendicular force is measured in newtons. Distance is measured in meters. It's the distance from the axis of rotation. Think of it as like the radius, okay? And our unit for torque is going to be a Newton meter, right? Now, I know you're looking at torque and saying, geez, Newton meter. Yes, it's very similar to our energy and our work in the sense that we're using a Newton something. There, when we talked about energy and stuff like that, it became Newton seconds and things along those lines, okay? So, all right, I know you don't have neighbors, but you're going to humor me with this, all right? So what you're going to do is you're going to put your arm out straight in front of you, okay? What we're going to do is then you're going to push down on your hand. Now, you know this is coming, so you can try to resist it and apply as much force as you want, right? Should be pretty easy, okay? Then what I want you to try and do is move up to your elbow, all right? And now see, is it as easy? Do you have to apply as much force to that spot, all right? What you should see is that the farther out you go, the less force you have to apply to get your arm to move downwards, all right? The closer up you get, the more difficult it becomes. The other thing you can do is go to a nearby door, all right? Open it just a little bit and then try and push way away from the hinges on it, okay? That push should be really easy the farther away from the hinges you go, all right? Now, if you want to, go nearer to the hinges and now try and push on that door and see if you can get it to open, all right? Now, a light door, really easy. If we were in my classroom trying this, with the heaviness of my door, so the closer you get, it's borderline impossible to move that door if you're right next to those hinges, okay? But the farther out, obviously, we can move that easier, all right? So, think of lifting objects, right? So, a few weeks ago, I had to bring some salt in for my water softener, right? And those are 40-pound bags. So the question becomes, how do I hold those water softener salt bags at 40 pounds? Or a dog food bag at 40 pounds, whatever you may have, right? Are you going to hold it way out here? Or are you going to hold it closer to your body, all right? So when we see this now, right, what we're able to do, oops, sorry, let me go back. So for us, we can hold more weight kind of, closer to our body, right? I mean, we get a certain amount that we can hold here, but actually I think you can probably hold more out there, all right? Anyway, all right, so determine torque for us. We need to define the pivot location, also called the fulcrum, all right? That's a big deal. So pivot point, when we're trying to lift that stuff up, is going to be different, right? When we think about it, trying to lift here, it's really tough. It's really, really close, right? Okay, yes, we can hold stuff better here, but as far as lifting, if we're lifting it up really close to our body, it's tough. If we're out here, now we get the full use of kind of our muscles and we're able to lift a little bit more because we're a little further away from the fulcrum, okay? Usually the fulcrum is a pretty obvious point, all right? Meaning when we're talking about sliding that door, that's a hinge, we can see that. When we're talking about lifting an object here, that's our shoulder, all right? When we're talking about, changing that tire, that's the bolt or the nut on the tire, okay? So what we start to see is that our axis of rotation here is going to be, in this case, the hinges right here, all right? So F perpendicular is a perpendicular line from the axis, or to a radial line from the axis. What that means is the radial line is just basically this straight line right there, okay? So when we look at our F applied, that's going to be our radial line from the rotation spot that we're looking at, all right? So what we can do is we can see these are two different ones, right? Here again, the one on the right, that's a knuckle buster. You're going to slide off that thing, okay? And if you've ever had to try to open a door and all of a sudden you push on that door and your hand slides and you hit it with your shoulder, that's what we're looking at right here, okay? So for us, the actual F perpendicular is a component of that, all right? So here on the left, the F applied is the perpendicular to the radial line. Over on the right side, though, it's a component of it. What that means is that it's part of it, and we have to calculate it. Not all the applied force is going straight into this wall or into this door, all right? So then we have to be able to say, okay, what component of it is that going to be, all right? On the left side, we're going to have all of that force turned into torque. On the right side, some of that force is going to be turned into torque. Some of that is going to be turned into slip, right? So what ends up happening is we have less torque on the right side, okay? So we're going to calculate the torque on a door with an angle. Now, here again, when we look at this concept of if this were straight into it, this is easy. So if we said, hey, this torque is going just straight in like that, okay? Well, that's going to be 300 times 2. That's 600 Newton meters of torque, okay? In this case, because it's on an angle, what we have to do is we have to find the component of that amount of force, right? And actually, I'm drawing this all backwards, aren't I? Whoops, sorry. I'll come back. It should be up here, right? Not down there. Okay? So for us, the pulling on the door, what we see is that this vertical component becomes extremely important for us, all right? So what happens is if we want to find this perpendicular force, we need this straight line going upwards, right? Now, on this side of the angle, it's tough to understand what it's going to be. So what we can do is we can look at it as it is also over there. Now, there's two different ways to do this, okay? If we've got the angle here, what we can do is say, all right, that's my hypotenuse, meaning they're applying a 300 Newton force that way, okay? As I look at my angle over here, this is my opposite, all right? So if I'm looking at my opposite and my hypotenuse, that's where I'm going to start using this concept of sine of 60, okay? Because that's the component that's going to be vertical. Now, if you don't like the sine, well, then I know that this is a 90-degree angle, right? So I could say, hey, that's 30 degrees there. Now this becomes the adjacent, and I could use the cosine of 30 there as well, all right? The angle becomes unimportant for us as long as we know the side that we're trying to get to. So if it's over here and we're opposite of it, we're going to use sine. If it's right next to it and right on the side of it where we need that perpendicular force, we can use cosine. You'll find that those numbers are exactly the same, okay? So we take our applied force of 300 times the sine of 60, which is like 0.87 times 2, and we find that our torque is 520 Newton meters. Now, is that different from our 600 Newton meters? Absolutely it is, right? All right. What we found was we lost 80 newtons of torque to that angle being different, not perpendicular to it, okay? All right, calculate the torque on this door, all right? Meaning that take a second, check it out, and then go ahead and see if you can punch this into a calculator. All right, so here again, we're looking at our component of vertical force, right? Or perpendicular force, I'm sorry. All right, in this case, if we just look at it as the angle is, we can do the sine of 25, right? If you don't like that because it's not in the perceived location that you want it to be, even though it is the vertical component, then change it. You know this is going to be a 90, so you could say up here, hey, if it's above this one, guess what? I'm going to do the cosine of 65, all right? So just to verify that, cosine of 65, 0.423. The sine of 25, boom, 0.423, right? And again, my calculator's in degrees, all right? We're not using any of that radians calculation here. That's only for angular stuff. Whew, thank the Lord, right? So if I know that, I can take either one of those two times my applied force, and it tells me what my perpendicular force is. Multiply that by 1.35, and we see it's 500 Newton meters. So 899.7 times that answer that I just got, times the distance that I'm traveling. So then my angle is 0.423. That's the cosine of 65 or the sine of 25 times 1.315. Boom, I get 500.002 newton meters. All right. Look for a little bit of homework coming out at you here, likely today. And then let me know if you got questions as we go forward. Okay? Otherwise, that's what I got. Talk to you.